humanoid brain. I'm Zach. I'm the lead for the humanoids or Atlas at Boston Dynamics. I've been at the company for about 15 years. Prior to leading Atlas, I led Spot. You want to say a little bit about yourself?
Yeah. Hi, Zach. My name's Alberto Rodriguez, and I joined Boston Dynamics about 4 years ago. Before that, I was faculty at MIT, about the time where I got very excited about the prospects of the humanoid journey. So I decided to step down and join the mission at Boston Dynamics. I started focusing on manipulation, and now I direct robot behavior in Atlas, where jointly with my colleague Scott Kindersma, we lead the AI strategy and oversee the implementation of that strategy for Atlas.
Cool. I got to ask, in the 4 years you've been at Boston Dynamics, what has surprised you most about the transition from being a professor at MIT to going into startup life?
Yeah, maybe one of the things that surprised me the most, and I don't know if it should have, but I actually have more day-to-day technical conversations now at BD than I used to have at MIT. Not because there's no technical people at MIT, which is many, but I just have more time for it. I used to be very busy with teaching and with surveys and with just doing random stuff. Mm-hmm. And now that's my mission, right? So I really enjoy that.
That pretty much mirrors my experience coming out of grad school, also at MIT, and coming over to Boston Dynamics 11 years earlier. Was when I was in academia. I was in academia because I loved building robots. And everything that I had to do that wasn't involved in building robots, I kind of dreaded. Going to class, reading papers, writing papers. I did it all so I could just be wrenching on robots and writing code on robots. And then going over into industry, you're like, wait, I get to do this all day, every day? It's pretty cool.
Yep.
So our vision for humanoids, essentially, is to build the world's first commercially successful humanoid robot, essentially solve manual labor in the process, kind of a big goal. We have a structured way of getting there. Strategy-wise, we really believe in general purpose hardware. So we're building a general purpose robot, a humanoid, general purpose hands, and that robot is going to be able to do just about any task in the world. But we're going to start easy. We're going to start in manufacturing, which is a pretty special environment, both because it's a great starting place and it's also crazy interesting. We're also going to build a robot brain. You can't really build a humanoid robot hardware generalist without having a humanoid brain that goes along with it. That's going to be the primary topic of conversation today, is how exactly we're going to build that brain.
You mentioned a couple of times general or generalist.
Yep.
Why general?
So I've got this video of Hyundai's plant at HMG Metal Plant America up. How about you tell us a little bit about what you see in that plant, and then we'll get into why we need a generalist for it.
That's one of the many car manufacturing plants we've visited, and HMGMA is one of the newest ones. So it has the highest ratio of automation. But despite that, once you visit it, you realize that there's still many tasks that are still, for the most part, done manually. And the first thing that comes to mind when you visit that plant is that those tasks are, on one hand, very hard, very complex. There's tons of variability that comes with adapting with the large variety of objects that go into assembling a car. Tons of very dexterous tasks, like using tools, assemblies, handling small parts. But if you talk to manufacturing engineers, they will tell you that the reason why they're not automated is not because of how complex they are. They have great solutions, lots of technologies to automate it. It's just, it takes too much space. It takes too much engineering, too much cost to automate each one of those. There's just too many, there's thousands. So a special purpose solution for each one of them is just not economically viable.
So there's the conventional manufacturing automation world, where if you want to, say, bolt a wheel onto a car, you would commission a machine that bolts a wheel onto that car. And that machine probably has a general purpose robot arm in it, but it's still a thing where you're going to write a specification. I want my wheel bolter runner machine. And a bunch of manufacturing and automation engineers are going to design that machine for you, make a special end effector for that arm, and install it on the line. There's going to be a vibratory bolt feeder, and all the stuff.
You're going to need tons of specialized programming to make the machines work.
Yep. And so, like, when you look at a car plant, we're looking at a bunch of tasks from real Hyundai plants here. There's probably tens of thousands of different tasks that need to be done in that plant. And the thing that you really rapidly get to is if you're going to design automation for each of those things, you'd be spending way more than it's worth to automate those tasks, and you'd probably be well into the next century.
Like an average estimate of like how long it takes for any one of those integration efforts, it's in the order of about a year and north of $1 million for any step that you want to automate. That's sort of the state of the art today.
Let's talk about how the tasks that we see in a normal car plant break down. You kind of have, well, really, really simply, I'd say you have material handling tasks, and then you have assembly tasks, right? In those material handling tasks, like the plant words, they would call those things like sequencing, kitting, racking, moving material from the warehouse to line side. And then assembly is like we were talking about, attach the wheel to the car and put the bolts in and all that stuff. What are the high points of those tasks to you?
I think that, while those are clearly different, the level of dexterity that is necessary to execute them is different. One is mostly about picking and placing and inserting parts in containers, while the other one has to do more with very dexterous part handling. The biggest source of complexity is the large variability, which is shared by both, right? Like you were saying, a car has like tens of thousands of parts, all of them different. And in the same assembly line, you might assemble between 5 and 10 different types of cars, each one with its own trim and each one with like 10 to 20 different colors.
So, and you turn over the model year every year. So
exactly.
You change a bunch of trim parts, interior technology and stuff. And then you do a major model line refresh, say every 5 years.
So it's that variability that really puts a ceiling to like traditional automation, right? The core question is, how do we make something that is more flexible, that provides a degree of generality so that you can automate those tasks?
Yeah. So how do we make something more general?
That's a $1 trillion question. Let me maybe backtrack 1 second before answering how we make something more general and describe how we make something that is more specialized. It's not that long ago, right? If you backtrack like 4 to 5 years, this is how robots, even humanoids, were programmed.
Yep.
Right? So you basically have 3 to 4 core workflows that are necessary. Like you model your assets, you model the parts that you have to manipulate, you model the environment that you're going to operate in. You build perception systems that are capable of recognizing and perceiving those parts and those environments. Then you build skills that are capable of handling those parts, manipulation skills, like let's say in a logistics application, it would be picking those parts or extracting or inserting those parts from the containers where they're contained. And then you build on top of that an agent that is capable of going sequentially between the steps of the task.
So yeah, and when you say build the behavior, that you made it sound pretty easy, but what is the actual work in doing something like getting a robot to say, we showed a video of moving engine covers around. Like, what is involved in getting a robot to like reach in there and grab that engine cover?
Yeah, in practice, what that means is you have engineers that have the right intuition to program how the robot should approach those parts and what's the right way to, let's say, position your body with respect to the environment to be able to reach far enough to extract it, to hold the weight. So there's a lot that there's a cycle that has to do with using human intuition in the form of expert robot programming, testing, finding failures, iterating, and getting that system to have high performance.
Cool.
Now, there's obviously an issue with that model, which is a scalability, right? Like, it's a system that if you have to deploy 3 times, you can do it. If you have to deploy thousands of times, doesn't scale fast enough. Work. And it's a system that also doesn't improve over time, doesn't accumulate experience and knowledge to make the next time easier.
So that obviously isn't going to work. So we've built a robot hardware generalist, and the world you described there has a large team of highly credentialed robot engineers, program it to do each task, just not going to work at its face. So we've decided we want to build this robot generalist, or we'll call it a robot brain.
Yep.
Because that's essentially what it is. How do you build a robot brain?
I think that the core part of it's still pretty similar to that cycle of refinement.
Mm-hmm.
The core difference is that you don't want to program the robot explicitly. Instead, you want to teach the robot how to do a certain task. And as the robot is doing it, you want to tell it when it has failed, how to correct for mistakes, how to improve its performance over time. So there's a core workflow there, something that we refer to as post-training, where basically you demonstrate the robot how to do something, and a certain number of times. It could take in the order of a day, for example, of demonstration of an expert demonstrator to tell the robot how to do that task and how to correct for certain errors that might happen during the execution, and accumulate all that knowledge now not in the form of a program, an algorithm, but rather in the form of knowledge ingrained in a neural network.
Okay. So that post-training step that you just described there, you said, some number of demonstrations. So like, let's say generously takes a day to learn how to, grab that engine cover and move it to the other slot. That's still awful lot of days to do these tens of thousands of different tasks. So like what are we going to do about that?
So the most interesting part of this new strategy is what we call pre-training, which basically accounts for a system that makes a good initial guess as to what should be that policy, so that once you go to factory and do the first deployment, the behavior is already somewhat good, and it takes a small amount of time to improve it. Now, the big question is, how do you build that system that is capable of producing a good initial guess, that has accumulated enough common sense and general understanding of what it means to move and manipulate objects and do tasks like manufacturing tasks, so that is capable of that.
And so what you're describing there isn't like some unsupported fantasy like that.
No.
That's essentially how modern LLMs work. So like this is how something like ChatGPT is built.
Yeah, exactly the same way. There's core differences because of the complexities around actually generating and finding the right data that is capable of providing understanding of visual, spatial relationships, dexterous manipulation, agile whole body coordination and motion, which is not something you find in text or in audio or even in video that is specialized for robots. But the techniques, the technology is essentially the same.
So something like ChatGPT is built on kind of the sum of all human knowledge on the internet.
Yep.
We don't have the sum of all human physical behavior available somewhere. So how do you get that?
So there's 2 parts to it. The first one is we have what I call data swim lanes that generate good data that is useful to capture that general understanding. Teleoperation is one of them. So scaling up teleoperation so that you don't solve one task, but you solve hundreds of them, thousands of them, not necessarily during deployment in factories, which is more costly and more difficult, but in a dedicated space where you do that. That's one bet. And to some degree, that's what most companies are doing today. Mm-hmm. But then there's other very interesting directions which I would qualify closer to research efforts today that provide ways to scale up data generation much faster. One of them is reinforcement learning in simulation, where you don't learn necessarily by providing optimal demonstrations, but you let an agent to explore by itself, trial and error, and optimizing behaviors. Since we can scale simulation to a much larger degree, that can provide a way to increase data generation. And the third one is directly by observing human behavior. If you design a robot that somewhat mimics or somewhat gets close to how a human operates in its form factor, in its hands, you can learn some degree of common sense of physical behavior from observing humans. And then there's a second way by which we can accumulate knowledge at scale in this pre-training phase, which is what we normally refer as the data flywheel, right? So once you've done this for enough tasks and you get to deployments, the data that gets generated by those deployments is very rich, is data that actually represents the environments and the tasks where you want your robots to operate. Mm-hmm. So that generates information, data, experience that goes back into pre-training. In a way, why it's important to get in the short term to be able to do deployments, even if it's without robots being yet, or the robot brain yet being perfect.
So that's the process that we want to execute. And those are the kind of data inputs we need. Mm-hmm. There's the matter of like what kinds of ML models are we training here? There's like a lot of different things floating around. Yeah, there's LLMs, there's VLAs, there's VLMs. Do you want to walk us through a little bit of a map of kind of how robotics was previously in the world we're headed to?
Yeah. So there's like a spectrum, right? So classical robotics, like 4 years ago, we built specialized models for, as I was describing earlier, for perception, specialized models for high-level coordination, specialized models for manipulation, even specialized models for mobility. Now, we've agreed that maintaining and evolving all of those models with all that complexity is not a scalable process. Yep. On the other end, you have a fully end-to-end solution where robots ingest pixels or raw information from sensors, and at the output, you produce torques or currents that go to the actuators. Yep. We know how to train these more abstract systems through experience. The complexity is the scale of data that is necessary, right? And like LLMs today are a perfect example. If you have enough data, you can rely on raw representations, like not just LLMs, but like video model prediction systems, right? You can rely on raw representations to train really highly performant systems. What's the degree in between where an actual practical solution is going to land on, for example, for manufacturing? It's still a question, right? Like you might want to benefit from the fact that manufacturing provides a little bit of structuring. So you know which objects are going to be ahead of time, you know the furniture and fixtures you're going to encounter with. So you might want to put that into pre-training. Yep. So in that spectrum from fully model-based to fully end-to-end trained, there's different progressions of abstracting more and more layers of like perception, high-level cognition, dexterity, and mobility.
Got it. So like in the large behavior model video and the associated paper with it, like where in that progression is Atlas at that point in time?
So that's a great example. That is not a system that ingests pixels and outputs torques, right? It's a system that ingests pixels and it outputs commands to more abstract representation of what a robot should do. So it provides commands for what the end effector should do, what the feet should do, what the hands should do, yes. Hands, feet, and torso should do. Below that, we have a very powerful whole body controller that consumes that and realizes that on the robot.
Yep.
Right? So that provides a layer of abstraction that makes learning simpler and reduces the amount of data that we need to generate, but still allows us to exploit the high agility and strength of a humanoid platform like Atlas.
I mean, that's tricky because like that's not just a technology progression thing. Like there's real frequency separation between what Atlas is doing, like with its actuators, versus like looking at a scene and deciding what you need to do next. Like, is it necessarily a given that should be one neural network?
No, absolutely. It's not a given that it should be just one single neural network. In fact, it is pretty common for especially dynamic balancing robots like humanoids or quadrupeds to rely on what we call system 1, system 2 separation, where you have a system at the lowest level, which takes care of whole body control, that the system that needs to run very fast and needs to know and understand sort of the extent of the strength and the balance of the robot. It needs to know that you shouldn't move your hand too fast over in this direction without counterbalancing with your body.
That's like in humans, that'd be like your cerebellum in your nervous system.
So it's unclear that you might want to force everything else in your system that is in charge of acquiring common sense to also have to learn that at the same time.
Yep.
So there's some value from separating that.
Let's jump in and talk about some of these data sources in a little bit more depth. So let's talk about teleoperation.
Yeah, I would say that teleoperation is today the most valuable source of data for early deployments or for early behaviors, right? So if you want your robot to exert a certain behavior in the next couple of weeks, teleoperation is your friend. It's the most valuable kind of data because it's fully embodied, right? So teleoperation means that you are controlling the robot and the robot is experiencing what it means to do a certain behavior. So the data that you collect, that experience, is through the body of the robot. So in a way, there's like zero gap between the demonstration and the actual data you're collecting.
Why is that important?
That's useful because that kind of data is not polluted by artifacts of your interface to the robot.
Okay.
It's like ground truth data, right? Like if it worked, it means that the robot will be able to do it again by using the same commands, sending the same signals to the actuators. So that data is valuable. It's probably the hardest to scale because it requires building a very proficient teleoperation system, right? So our demonstrators at BD, they learned over a few weeks, they become experienced in understanding the extent of what Atlas is capable of doing by spending hours moving robots through this teleoperation system, which basically is in the form of a VR system where they see through the eyes of the robot and they have trackers in their body so that the robot reacts live in real time to the same motions that they're doing. Once they become experienced in doing that, they are free, so to speak, to command the robot and get it to do anything that teleoperation interface allows them to do with its observability.
There's the scale thing going on here is important. So like we're talking about trying to build something like an LLM for physical movement of a robot. Again, those are trained on close to the entirety of human knowledge. And we're talking about collecting, thousands, tens of thousands, maybe, generously hundreds of thousands of teleoperation, motions and hours of data. There's a immense scale gap between what we want out of these models and that kind of data source, right?
Yeah, that's correct. And it's not a secret, right, that that's probably not going to be sufficient. We think that it's still very valuable because of that sort of zero gap transfer between the data we're collecting and the behavior, the motions that the robot can execute has tremendous value when it comes to demonstrate embodied behavior So if you want the robot to crouch, if you want the robot to reach, if you want the robot to do whole body coordinated motion, it's a great way to generate high quality data.
Yeah, and it's definitely how we're going to pilot the giant Atlas to fight Godzilla.
Yes, exactly. Will you be inside?
No. Someone much better at it than me will be. All right, let's talk about that second kind of data then. So you mentioned reinforcement learning or trial and error for manipulation. What's going on there? How does it work?
So reinforcement learning in the scale of high quality data, it would be below teleoperation because now you have this sim to real domain gap. The data you generate in simulation, it doesn't translate perfectly to the robot. We're pretty good at Boston Dynamics of understanding that sim to real gap, but there is still a gap.
Mm-hmm.
However, simulation gives you the option to scale massively the data generation workflow, which is a great benefit, but also allows you to control the scenarios where you're learning, right? You can expose the robot to small variations of anything you want in a controlled manner. Oh, you want to grasp this object? Well, do the same thing, but also if the object is 1 centimeter to the right or 1 to the left or in thousands of variations.
Mm-hmm.
And in that context, and because of the massive scale, we have access to algorithms that are very hard to replicate with real ground and real data or with real hardware, which are algorithms that are based on trial and error and optimization to fine-tune behaviors that become better and better over time, that can become even better than demonstrations, just because they're trying to maximize some objective.
Yeah, so I guess that's an important thing that we didn't quite hit on earlier is with teleoperation, you always have this interface that makes it a little hard to do really precise, really fast, really dexterous things. You're saying that that's really not a thing for reinforcement learning.
Yeah, actually, that's a pet peeve of me that I have with teleoperation, which is that we use teleoperation to provide high-quality demonstrations that are meant to build this physical understanding of what it means to move in the world. However, demonstrators, unless they're very, very skilled, because of the complexities of the teleoperation interface, they end up demonstrating behaviors that are somewhat subpar. They are like kind of slow or too sequential. Instead of using dynamic behaviors, they use quasi-static, slower behaviors. And it requires conscious design of the teleoperation interface, but also conscious training of demonstrators to avoid that.
Mm-hmm.
Simulation or reinforcement learning doesn't have that limitation. You can sort of optimize the performance of any given task to its maximum. You can force it to be fast and dynamic, and you can force it to be robust by exposing it to many variations. And we've had we're very happy with the success we're having in that direction, in particular for dexterous manipulation.
Yeah, so you have some pretty cool examples here of 3 tasks that our reinforcement learning folks just trained up recently. You want to talk about those 3?
Yeah, so we have here examples that are sort of like the bread and butter of what it means to do work in the assembly line. So insertion tasks that are haptically driven, like inserting a steering wheel in a socket, or inserting a plug into a socket, or inserting a small part into a jig. Any of those tasks is very, very hard to teleoperate, either because it requires small, very controlled finger motions, or because it requires sensing haptic signals that are not directly visible.
And so, like looking at these look like specialist policies. Like you trained a thing that specifically only knows how to pick up a steering wheel and put it on the steering column. How do these end up part of this robot brain we're trying to train?
Yeah, that's a fun question. So that's correct. Each one of these is its own individual policy. We call these specialists. They're really good at doing one thing, with its domain of generality or robustness, but it's that one thing. And we're very excited about the fact that we can scale that process pretty seamlessly of creating thousands, tens of thousands, hundreds of thousands of specialists. In a way, these become your teleoperated examples, right? If you do rollouts of these policies, this generates a kind of data that then you can condense into a generalist like you would do with behavior cloning teleoperated data.
Cool. And then it not just manipulation, but also the locomotion end of Atlas too?
Yeah, absolutely. Right. So locomotion, especially agile locomotion, if you want to go fast, if you want to do natural walking behaviors, if you want to do cartwheels, suffer from the same issue. It's very unrealistic to expect we're going to get one of our demonstrators to get Atlas to do a cartwheel.
Yeah.
That's something that you really want to optimize through because it's a dynamic behavior that has very contrived regions of attraction of where you need to get the robot. You need the robot to accelerate to a certain velocity so that it can jump and do a cartwheel. It's not something you want to do other than in simulation.
And then this third kind of data, human demonstration or human observation data, what does that mean?
That's the biggest bet, I would say. It's the more long horizon bet, but also the one that has highest potential of scope. So it means anything from like all the way to learning directly from YouTube videos, right? So can you get robots to learn what it means to interact with the physical world with dexterity and common sense by looking at videos of people repairing bicycles in their backyard or looking at videos of people constructing things. So that's the extreme of it. But there's a spectrum of ways in which you can use more open-ended demonstrations from people that doesn't have to be all the way to teleoperation. For example, something that we're very excited about is egocentric demonstrations where you get people to wear sensors that make it easier to capture what the person is doing. It could be the same sensors in the head that Atlas has in the head. It could be gloves on the hands that capture tactile signals and just get them to do by their own life or get them to do their own job and just learn what it means to do that job from that data.
Cool. And that does sound like, or rather the reinforcement learning in that one do sound like the kinds of things that conceivably could get to these scales of data that are being used to train LLMs.
Yes, agree, both of them. And I would say that it's not necessarily either or. Each one of those two has their own strengths and weaknesses, right? So clearly simulation, from our experience, is a really good choice for dexterous manipulation, but it might be more difficult to learn things that involve highly deformable, interacting with highly deformable objects, for example, because they're just naturally difficult to simulate or require a lot of compute. Direct egocentric demonstrations with people wearing sensors, they're great at capturing just like the breadth of common sense of what it means to interact with objects and the sequence of things that you should do to accomplish a certain task. But it will be more difficult to learn directly from that dexterous manipulation because they're not embodied in the body of the real robot with its own sensors.
Cool. Okay. So we got a complete plan to build a robot brain.
Yeah, we should. Now we just need to execute.
So let's go back and recap. What does it mean to build a generalist, and what are the essential characteristics of that thing, or what are the characteristics that thing will have to have for us to be successful in putting humanoids to work?
I would say that there's 4 core tenets, right? So general purpose hardware, and you've talked about it. Ease of retasking, very important, to avoid the issues with the cost of integration of every single task. Ease of retasking and getting to a point where It's not months, but rather it's days or hours what it takes to get a robot to do a certain job.
Yep.
Natural interfaces for interacting with the robot rather than requiring expert programming. Us and our customers will want a more natural way to tell robots what to do, either with natural language or with direct demonstrations. And the fourth one, safety around people.
Did you get reliability in there?
Yes, I did not get it, but
So we got 5.
Let's say 5.
Yeah. So we're building this general purpose robot. We're building a general purpose robot brain. In conjunction with that, one of the really cool things about working with the Hyundai Group is we're not just building this robot in a vacuum. Like we're also redesigning car plants and redesigning general manufacturing facilities alongside understanding what Atlas's capabilities will be. Can you tell me a little bit about what's exciting about that to you?
Let's say one thing that, maybe 2 things. Yeah. The first one is that I think working with Hyundai has made the mission very clear.
Yeah.
Right? Like our mission is to transform manufacturing. And once you know that that's clear, it relieves a lot of pressure and stress of like actually thinking and dreaming about any other application domain where you could also be working, which there are many, and which we might go also after. But what's non-negotiable is that we need to solve and transform manufacturing. So that has been, I think, exciting to me, the fact that we have a clear mission, which is very hard, but it is clear.
Yeah, that was honestly one of the hardest parts of the early days of Spot was, we had this amazing robot and we had so many application ideas for, what it could be really, really useful for. Like today, we look at Spot and we see it being used all over in these industrial inspection applications. And it seems obvious now, but like in the early days, we were spread really thin between so many different applications, testing and trying to do demos of each of them. It's really, really refreshing with Atlas, knowing that, if we can just solve this manufacturing problem, that we can be successful. And then we can go into the rest of the stuff. We can... Exactly. We're not going to stop at manufacturing. We're going to do curb-to-door delivery. We're going to put robots in your home, clean your tables, make your bed. But we know which one we have to do first.
Exactly. Yes. Yeah. I mean, at the much smaller scale, personally also, like before joining BD, I was faculty at MIT. And as faculty, the journey is always about finding the right motivation to solve the problem that you think you should be solving, right? Like you always have to convince yourself, actually, am I solving the right problem or am I confused? I should be solving a different one. So the change to BD has been refreshing also because of that. Like I don't have to ask that question myself anymore. I know what problem I need to solve.
Yeah, I feel the same way. So part of the reason why we're talking about this today is we need more folks to join us on this mission, building a humanoid robot brain. Can you tell me a little bit about what it's like day to day on our machine learning team?
Yeah, absolutely. Like that's the largest area in Atlas where we're hiring people with experience on building large behavior models and people with experience on reinforcement learning. The experience in the team, I would say, is it's hybrid, right? So there's some people in the team that are very excited about research and they spend their time solving the problems that we know we will have 3 years from now or 5 years from now. But there's also people in the team that are very enthusiastic about how can we get as fast as possible to deploy these robots for real. And that is also people that need to be very experienced on these modern techniques like behavior cloning, like efficient data collection techniques, like efficient co-training techniques to fuse data between simulation and teleoperation that also are good roboticists, right? So the experience, I would say that it's on both sides, and we're always looking to hire good people.
What do you think your team looks forward to and enjoys the most day to day?
I think the team is very excited about, I don't know if the team, but myself, I am very excited about the prospects of really enabling dexterous manipulation.
Mm-hmm.
I think that is the ultimate frontier of what it means to do general purpose work. BD is a place where you get to experience both the design and fabrication of high-end dexterous grippers, and you get to experience the development of the techniques that are going to get those grippers to do very cool things, like using tools, like handling objects. And to me, experiencing that and seeing that sort of rapidly progressing, it's fascinating.
I got to answer this myself. I have so much fun. The really special thing about robotics, as opposed to any other place that you could be working in machine learning or really in any of the functional disciplines, is that like we do the whole thing. Like, so you mentioned, folks at Boston Dynamics design grippers, and like if you're a machine learning researcher, you get to talk to the folks that design the fingertips day to day, argue with them. You get to see your stuff show up in the hands 3 months later. And it extends all the way through the other side too. So like we have folks who work on robots day to day, diagnose things. We also have folks who sit 15 feet further away from the robots in the lab who think about, how do I wrangle 1,000 GPUs to run this training job faster? Like you see every aspect of putting a robot together all in one room.
Yep.
I don't think there's very few places in the world where you can get that.
It's very exciting.
Well, thanks, Alberto. Thanks for telling us what's going on the ML side of Atlas. And then we'll have to see how fast